All right. Hello and welcome to another exciting episode of ARMS Innovation Coffee. And as you may have noticed already, my co-host Alessandro is not here today. He is unfortunately having some power outages, and you're stuck with me. So I'm very excited about this. We do have a really cool episode. We'll be meeting with some folks from Edge Impulse. We've had them on the show before. We also have some folks from Raspberry Pi here. Also, we've had some very cool episodes with Raspberry Pi, but we do have a new guest today, and we're going to talk about some very exciting news. In fact, I'll tell you who our guests are now. So we're joined by Zach Shelby, CEO at Edge Impulse. Daniel, and I'm going to try to say his last name here, Sitanayaka, founding engineer at Edge Impulse, and he is also an ARM innovator, so very cool. And Alistair Allen, technical documentation manager at Raspberry Pi. Now, I'm very excited about these guests. Of course, we have a whole bunch of cool stuff planned for you. If you have questions, you can always post those in the chat. We'll also be providing some updates that will complement Nvidia's GTC event that's happening right now. And then we're going to be showcasing a really cool demo brought to you by Daniel, who is one of our guests here. Now, remember, if you like the video, make sure you smash that like button and don't forget to subscribe to the ARM Software Developer YouTube channel after the show. Before diving into this segment, I wanted to also quickly talk about last week's episode, which we usually do. We were joined by Michael Gielda from Renode, which is an Antmicro company. He's a business development and co-founder of Antmicro. He talked about a whole bunch of cool stuff. I don't want to spoil it. So if you didn't get a chance to watch last week's episode, after this stream, cruise on over to the ARM Software Developer channel and, basically go watch that episode if you have an extra hour in your day. So moving on here, let's get introduced to our guests. So I'm going to bring them on right now. We'll put them in order here. Let's see. So Zach, Daniel, and Alistair. Hello, everyone. Welcome to the show. And thank you so much. Hello. Yeah, welcome. And thank you so much for taking the time out of your day to join us here on Innovation Coffee. As our tradition usually goes, I know that, we've already had you on the show, Zach, before. We still like to kind of give you a quick minute to introduce yourselves and let the community know who you are and what you do with Edge Impulse and, of course, Raspberry Pi. So please, Zach, go ahead. You're first.
Awesome. Thanks, Robert. Hi, everybody. Zach Shelby here. I'm the co-founder and CEO of Edge Impulse. We have a long history working with developers. Myself, my co-founder Jan, many of the people that I work with, and something that I've always been fascinated by is kind of the invisible computer, how embedded compute is running the world. If think about how it runs industry, manufacturing, producing and distributing the vaccines that we're now dependent on with the pandemic. Embedded compute's really everywhere, and it's all these computers that you don't see and are just churning away and doing their job. Already since a child, that really inspired me, and that's how I got involved with the Internet of Things. Ended up spending some time working at ARM, and then that's why we founded Edge Impulse as well, right? Like finding ways to enable machine learning for more people, more developers. And I don't even think about it as machine learning anymore, right? Like machine learning is just a tool. I really think about it like data-driven engineering. How can we enable people to use data to drive all their different engineering tasks, right? Developing new algorithms, new solutions, new things, like in parallel to coding. So that's something we can talk about today as well. Like how is innovation changing because of ML?
Yeah, that's awesome. Actually, you've done so much stuff in the tech space. I'll remind everyone who's watching right now, if you have some questions for Zach about anything that he's done in this space, if you are familiar with him, please feel free to post those. We can bring them to him. But yeah, Zach, thank you so much for the intro. So on to you, Daniel. Welcome.
Hey, thank you, Robert. And hi, everybody. My name's Daniel. Whichever you prefer. But I work at Edge Impulse. I lead TinyML R&D. So basically figuring out how to get deep learning models and classical ML models to run well on tiny little devices. And so that ranges everything from like Cortex M0 devices, like super low power, very cheap, little bits of silicon, up to big ML accelerators with embedded Linux running, which is one of the really cool things that we've announced this week. So I could say any number of things about this field. I think it's the most exciting place to work in technology right now, and it's even going to get more crazy over the next decade. This is the technology that's going to be transforming the fabric of the human built environment, and the big thing that you're going to be interacting with every day that you never expected 10 years ago. So I'm very excited to be part of this and to share this with all of you.
That's awesome. And real quick, do you want to give kind of a quick like sneak peek of the demo you're going to be showing us later so people can stick around in anticipation?
Yeah, absolutely. So what we're going to be doing is showing how easy it is with the type of technology that we're working on to train a model that can recognize different objects in a stream of video and then run that model on an embedded Linux device. So I'll be showing you everything you need to do in the space of a few minutes, and you can literally go off and follow a tutorial and do it yourself.
Very cool. So definitely stick around if you're interested in watching that demo. Thank you, Daniel. Last but not least, Alistair, you're up. So welcome and tell us who you are, what you do.
Thanks. So my name's Alistair Allen, and I get bored really easily. I started off my career doing research into high energy physics of the collision shocks around accretion disks on white dwarf stars, and then sort of just gradually drifted sideways into playing with the toys. I spent a lot of time working with agent-based systems to solve scheduling problems for robotic telescopes, and that led me into machine learning and what later became known as big data. And I spent a lot of time investigating what people refer to as the data exhaust, and the data that lives outside the cloud, distributed through embedded devices. And as a consequence, I did a lot of work on mobile systems. I actually was, along with Pete Warden, who I'm sure everyone listening here knows well, was principal behind one of the first big mobile privacy data scandals. Anyway, that sort of led me to think and work on what's known as the Internet of Things. And I sort of drifted into embedded systems. And that led me to essentially be in charge of all the technical documentation at Raspberry Pi. And all of that sort of made sense at the time.
Well, that's great. In fact, we've been talking. So we've had Raspberry Pi folks from Raspberry Pi, Eben Upton. We were joined by Gordon Hollingworth. We've been joined by several folks from Raspberry Pi, and every single time, the technical documentation comes up, right? Because Raspberry Pi really is, I want to say, someone or an entity of documentation that a lot of companies look up to. So I have to give you my respects. You've done something right.
I've only been here a year. I got brought in specifically to make sure that Pico and the RP2040 was well documented, and it was a solid place people could build on. So I can't take credit for anything before that, but
that's all right.
We'll get better.
Yeah, that's all right. That's awesome. Cool. So welcome everyone once again. Very exciting episode ahead of us. I want to kickstart this off with a question for Zach. We're going to dive right in. We mentioned that there's an exciting announcement, some exciting news that's happening this week. And Zach, why don't you take that away? What kind of exciting stuff does Edge Impulse have going on?
Yeah, so many of you will know us as the company that's made machine learning development for microcontrollers accessible for more developers. Think of us as democratizing machine learning as a development tool for everybody. And we went about doing that by kind of just rethinking the entire persona and the entire process of how you go about making use of data sets, training and inference deployment. In the big data science, big cloud ML world, the tools are very much aimed at data scientists, right? It's all like a data scientist, ML engineer world, right? All the tools, and then those people that use those tools go on to make more tools, and all of a sudden, all the tools are made for them, right? And what's happened is it's become a very fragmented space. Like you've got like 10 tools for data label funneling or data label routing. There's like 10 tools for that. There's 10 tools for data labeling. It's another, 8 frameworks for trying to manipulate the pre-processing and the training. There's tools like for very specific quantization things, et cetera, right? So in order to make machine learning work, you have to piece together tens of different tools. It's very, very hard. If you start to mix that with edge compute and embedded, right, the space that we come from, you have like a big mismatch of these two worlds. And so what we've done is rethink this, particularly for the embedded developer, for people working at the edge in real industrial systems, and thought about, well, what do they need to succeed with this? And so we flip this on its head and say, no, we don't want to piece together 30 different tools. We'll piece this all together and host this in a really nice infrastructure for the developers and for the enterprises they work for, in order to really make this a tool they can use quickly, right? Gather some data, train some models, feel confident that that's going to work, and then be able to deploy that on real hardware, right? Optimized for that hardware. That's the concept that we brought. So we did that for microcontrollers last year. We're part of the TinyML movement. But what we heard from the community, right, from the developers and from the enterprise customers is that, hey, we don't only work with microcontrollers, right? Like in one project, we might work with a Cortex M4, but the next week we're turning around and targeting a Linux device on a Raspberry Pi, right? Or we might work with Android devices or a whole spectrum of things. And we want to be able to deploy these machine learning models all the way through that range of edge compute. And we've heard that over and over and over. And what surprised us was that the experience for doing data set collection and doing inference deployment on embedded Linux was horrifically bad, right? The tools and the level of hacking you need to do. Alistair is, one of the leading, and I think he underplays himself. Alistair has done some of the leading work on profiling machine learning on these different types of embedded targets. Like, it is a massive amount of work you need to do to get this stuff working, and you really need to become a specialist. And so we were actually just surprised by the demand and the hunger there was for this in the Linux world. So we decided to go and extend Edge Impulse all the way through, not just microcontrollers, but through all kinds of Linux targets. And we partnered with Raspberry Pi to bring that experience to the Raspberry Pi. And our motto is, machine learning in under 5 minutes, right? We should be able to collect some data, use that data to train a model, an initial model, and then get that deployed with real, optimized, cross-compiled native machine learning inference on that device. That's what we're trying to achieve. And that's what we announced this week. It's really exciting.
Very exciting announcement. And I love how, you said, what you were doing last year, taking into account feedback from your partners, different companies, of course, the community. That is amazing. Very exciting to hear. And on that note, Arijit, one of our community members here in the chat, is like, question, what is Edge Impulse doing? Answer, everything. You guys are really tackling a lot of stuff here. So that's just very cool to see the evolution of Edge Impulse and what you guys are up to. So on that note, moving over to Alistair, you did bring him up. What does this announcement, what does what Zach just said mean to Raspberry Pi and the work that you're doing?
I mean, I think that the main thing that Edge Impulse is bringing to the table here is the abstraction, right? As Zach mentioned, right, actually trying to deploy these systems onto the edge, onto Linux-based systems is still quite hard, especially if you're using accelerator hardware or something that's using slightly non-standard hardware. And it's actually really hard to find tutorials on how to do inferencing, right? This is one of my bugbears. This is one of my bugbears about machine learning, which is there's actually quite a lot of tutorials on how to get started with TensorFlow. And they all stop right about the time you've trained a model. You train this model, this is how to get your data, you train a model, here's your working model, and it's just like, oh, we've stopped. And of course, the whole point about being a developer and wanting to use machine learning rather than being a machine learning researcher is the inferencing, right? And one of the things that the Edge Impulse announcement makes really easy is a cradle to the grave deployment. You can take data with a Raspberry Pi or your laptop or some other type of data source. You can train the model in the cloud using transfer learning, which is a really powerful lever. We should talk about that in a bit, but it's a really powerful lever. And then, which is really hard to do in the cloud, right? It's like the edge computing is entirely fast enough to run inferencing models. Like the Raspberry Pi is a really competitive platform to run my machine learning inferencing on. Training, not so much. I don't really want to try and train a large model on a Raspberry Pi. That's going to take a while. So being able to do you take your data in situ on the edge and then train it in the cloud and have your model back deployed onto a Raspberry Pi on the edge and then run it there. And, if necessary, unplug your network cable, right? Because that's perfectly possible with the Edge Impulse thing. Your model is now local. You can write your code and you don't have to talk to the cloud anymore. Which is the huge thing about edge computing and machine learning for me, which is the privacy angle. Because like one of the things I mentioned in my intro was like this mobile data privacy thing I got involved with, and it turned me into a privacy advocate just by accident, essentially. So the machine learning and the edge is to me the big advantage is privacy, and because you can do your training in the cloud and then use your model locally, that's what it brings. So it's good.
Yeah, no, we've addressed that in earlier episodes about, compute at the edge and why it's so important, but also the privacy factor is, just huge. And so definitely appreciate that. And, of course, if you want to talk more about it, we can. Real quickly, though, I do have a announcement here. I'm going to hit this little button real quick. Alessandro's power is back and he's on the stream. So Alessandro, you joined us.
Hi, everyone.
Yeah. There we go. Very cool.
It's amazing. I haven't been without power for a while, and I was looking around. I was like, what can I do? So I looked at my bookshelf and I found a book called Improvise. So I thought that would be a good book to read while power is off. so I was reading that and I'm back on. But yeah, awesome to see all you guys on, and a pleasure to be here.
Great. So we just got done talking about the announcement from Edge Impulse. And then, of course, Alistair chimed in on how that's affecting Raspberry Pi. On the next question, I don't know, do you want to take it away, Alessandro? We have a whole list here.
Let's do it. Yeah. So I mean, while I was away, I was actually thinking about the next what to ask you guys, and I think what's interesting is that something else is happening right while we're speaking, right? So there's actually an announcement workshop going on right now. Zach, Dan, do you want to talk about that? What are you guys announcing?
There's a story behind that. So Jan, our co-founder and CTO, who's a sneaky guy. Jan's pretty small, so he can fit in all kinds of small places. So he sneaked into Jensen's kitchen. So the CEO of Nvidia, he snuck into his kitchen, and he's right now giving a keynote talking about this, right? Talking about what we're talking about here. And of course, remember, keynotes and virtual events are semi-produced. So you can play back that keynote. You guys that are watching Innovation Coffee, you're not going to miss the keynote. If you've got GTC login, you'll be able to watch Jan's keynote anytime you want. So no worries. But Jan's giving a keynote talking about this this whole mission that we're on from Cortex M0 all the way up to embedded Linux, Raspberry Pi, and even GPU acceleration. And so what he's demonstrating is that, yes, we also have support to be able to cross-compile Edge Impulse model outputs to things like NVIDIA Jetson Nanos. Just using the CPU if you like, or using GPU as well if you like. Depends on the kind of model you're working on, whether that makes sense. So, but that uses the same framework, the same tools, the same thing that we're talking about here with Raspberry Pi. So that's what Jan's doing today. He did break into Jensen's kitchen. He'll get thrown out at some point, but that's the beauty of remote events.
I saw a snippet from that keynote on Twitter yesterday. I was like, that looks very fun.
No, I recommend it. Jan's always awesome to watch. So check out that keynote. You'll dive a little bit into technology, but we're going to dive into this technology live today with Dan, which is even cooler. So you're going to see how this stuff works, and we'll dive into some of the technical pieces around it, like transfer learning. One thing I did want to bring up from Alistair, when he just talked about transfer learning and models and inference, something that we've seen as a trend in this whole industry is like a big fixation on off-the-shelf data sets from research groups and off-the-shelf pre-trained models. It seems like this never-ending cycle of everyone uses the data set that everyone else used because they're all researchers and they're all trying to improve that graph, whatever that graph thing is that everybody follows in machine learning research. They're trying to move that graph. Is it up or down? I never remember which way is best. They're moving it the better direction, right? And so everyone's very, very focused on overfitting everything on these off-the-shelf data sets. And then they're very proud when then they're the only ones that can train these huge models like YOLO, for example, or even MobileNet that detect thousands of images out of the box. And then it seems like 99.9% of people in the industry then just use that model off the shelf pre-trained, and that's what they actually run on all these devices. So the big thing for me is really opening this up to custom data and like completely custom model training, like training a model that does a very specific industrial thing. Like we heard from an industrial customer, like when this machine breaks, there's red slime that like goes down this wall. Could you use computer vision to detect when the red slime comes? So it's like a very, very specific thing with custom data. So I think that's kind of the holy grail here, really. Like what the technology is trying to enable here is let's enable people to use really, really custom data and then train completely customized models and then really deploy those on these devices and kind of gain the benefits from machine learning without being stuck in these off-the-shelf things that somebody else thought that you might need.
So that's really interesting, because I've stood up on stage back when you could actually stand up on stage in front of actual like live human beings. I stood up on stage and argued that developers should mostly be interested in pre-trained models, that model zoos were vitally important, because we literally can't replicate those huge data sets. We can't replicate the cloud availability that Google or whoever has to train those huge models, right? That we have. So therefore, most developers aren't in. So it's a divergent from the open source thing. It's like, as developers, the thing that we're interested in is the source code, right? We want the source code so that we can replicate and build our stuff. But because we're not machine learning researchers, we're developers, the thing we're interested in should be the end product, the model, which, you know, you would think would be the binary of the world, but maybe it's not. But yeah, the transfer learning, until very recently, transfer learning has not been accessible, right? And I think that's one of the great things that the Edge Impulse stack does. I wrote a blog post for the launch that went up on the Raspberry Pi blog, and I was actually pretty astounded that I used the transfer learning to tell the difference between like a banana and an apple. I don't have a banana and an apple here. You know, it's like we're talking about machine learning. I should have a banana in my hand. It's like it's necessary. But it's like, so I took 10 images of each, and I used the transfer learning function to retrain this model, and I was really surprised about the sort of accuracies I was getting out the far end. And so yeah, I think it's one of the things that you guys are doing really well, which is that you're making transfer learning accessible. Because up until that point, I would have argued very strongly that pre-trained models were the thing that developers should be interested in, and not the data sets and not the training at all.
Yeah, it's a really good point. I think so much of the friction involved with building real applications with machine learning that has existed so far has come from the way that the field has evolved from a research field where it's all oriented around researchers trying to use benchmark data sets and come up with new model architectures that can get slight improvements in performance over what their competing research team did the year before. And the output of that being these pre-trained models that no one really understands how they work or how they're trained or what they're doing inside, apart from the researchers who built them. And then they're kind of thrown over the wall to developers who maybe can find a way to use them. But most of the time, you're really going to want to do something a little bit more custom. So unless you're doing something that fits into that world that researchers happen to have trained a model around, you're out of luck. So that's been the way things have been in the past. And there's a lot of barriers to communication between people who are in the field working, building products, building applications, and solving real world problems, and ML researchers. And it's nobody's fault. The people in the field don't have time to do a PhD in machine learning, and the people who are busy doing a PhD in machine learning don't have time to go and learn about the particular problem that a particular company has in its factory. But what we've seen now is the ability or the availability of tools like what we're building with Edge Impulse that allow developers who are working directly as domain experts to apply their knowledge to the problem using all of the fruits of this research, but with an easy to use tool chain that kind of connects the dots for you. So you don't have to be an expert. You don't have to have super deep knowledge. If you do, it can be helpful. But to get good results, you can come with your domain expertise, and you can benefit from all of the work that's being done by the research community. And there's now a pipeline that connects the two in both directions. And I think that's the stage we're in right now with all of this. That's why you've probably seen more and more about this type of topic over the last year or so than you ever did before, is because we've reached that point where the two sides have kind of grown together, and there's now cross-pollination between what's going on behind the scenes and behind the other scenes.
So did everyone's priority markers get hit? Alistair, was you up?
Yeah.
Take it away. Take it away. Yeah.
Oh, no, it was just a throwaway, which is that you see quite a lot of papers coming out of machine learning research groups talking about the energy it takes, the amount of power and like energy it takes to train models, and like what the return on your megawatts of power or kilowatts of power you're going to put into training this model. And it's just like, then they use the model once, right? And I can't remember which research group put out this paper. I've talked about it before, which is this paper that shows that, it uses the combined power of some American car for like its lifetime or something to run the model. And of course, they don't take into account, if you put this model in a little widget, then you build 1 million of the widgets, and then you send the widgets out into the world, then you have to amortize the amount of energy you've spent training the model into that number of widgets. And it shows the disjoint between the research community and the industrial community. And you see the same sort of disjoint in cryptography, right? There's a lot of cryptographers that talk about the theoretical way you could break an algorithm, and then you don't actually see lots of people breaking actual cryptographic data. And you see the same sort of disjoint. It's sort of interesting the way the background of where the field came from, I think.
So I think this is a great segue, and pretty much all of you have already addressed this question, but I just want to get final thoughts on it. Are we moving towards a future where Raspberry Pi developers or developers in general can just simply write code, develop models once, and then deploy it to pretty much all ARM-based hardware?
We're getting close. So the approach that we use, like philosophically, is a digital twin approach to machine learning. And that's not what everyone does, right? There are a lot of machine learning stacks that are very hardware specific. So you can see like machine learning tools from specific DSP vendors and other vendors that are like the complete stack is very high into the hardware. So it'd be hard to do. But our philosophy is, no, we really need a digital twin of the math. So when you're like working in Edge Impulse tools, the data set and the algorithms are independent of the hardware. So it is like virtual math. As long as your model is of a suitable complexity and size, we then do like an on-the-fly compilation pipeline. Think of it as like the on-the-fly deployment pipeline to the hardware of your choice. So for example, if you're going towards a Cortex-M target, we'll do different optimizations. If you're going towards like we also support exotic things, like Himax has a little computer vision board with a DSP. It's a pure DSP. So we do a completely different approach of DSP compilation and optimizations for that. Or we mentioned the Nvidia, like where we do GPU stuff, that would be a very different process. And we just in time take advantage of the hardware accelerations and other things that are there. So the tools that we then use to enable that, you had the Renode guys on last time, that's awesome. So we use Renode and a bunch of other mathematical estimation techniques. So in our tooling, we try to give developers an estimate of how big the model will be and how long it will take in inference time on this particular hardware target. So we have like a drop-down list of 10, 12 different hardware targets. And we do that like pre-estimation already at development time, because you want to get an idea. It's always like a huge problem for developers. Like, will this fit in my Raspberry Pi Pico 2040 chip? I don't know. Like, it's really hard to tell whether that would even fit there. So we try to give them that like indication. So what does happen is developers will kind of choose a different model size. Like we've got like 5 different mobile net transfer learning model sizes. You can choose different model sizes to hit your hardware. But we are moving, I think, towards that future where you will be able to deploy kind of like pretty flexibly across all this embedded hardware targets.
Yeah, just real quick to talk a little bit more about Renode. Hardware virtualization was kind of the theme last week, and I'm going to share the link in the chat here so that you all can go watch that later. But yeah, thanks for touching on that, Zach. Did you, Alistair, or Daniel want to add anything to what Zach just said, or should we move on to the next question?
Yeah, I just say there are 2 parts of this stuff that's really hard, right? The first part is the machine learning part, which is like a world unto itself. How to collect data, train models, get all the dependencies working on your computer to be able to run the scripts to train the models, and how to evaluate them and all of that. It's a universe of things. And then on the other side is another universe of things that maybe the viewers for our show today will be a bit more familiar with generally, because it's the embedded side where there's just as much skill and hard-earned wisdom and experience that goes into being able to set up a build environment for a certain board, or to be able to optimize code for particular platforms. And it's just as big a world, right? And so what we've been able to do is kind of connect those 2 worlds again, so that you don't have to have that expertise in both, because that makes it a non-starter. Very few people have that expertise in both. You know, in our company, we have some of the most knowledgeable people in these worlds that are out there in the industry, and there's no one who knows all of it, you know, apart from maybe Jan. But we're still kind of siloed in those domains, and you need a product and an overall experience and flow that can bring these things together to make it accessible to everyone. So like, yeah, the future where you can train a model once and deploy it to any target, it's nearly here. It's, you know, in some ways it is here, but it's really difficult to achieve. And there's a lot going on under the hood that makes it really difficult to try and do that yourself.
I mean, I think it's interesting to think about how long these models are going to survive in the wild. Back in the 90s, for those of you that remember the 90s, some of us perhaps, I worked for a large corporation that no longer exists. And I was training neural nets for image compression. Back when it was, you know, what was that, the second time neural nets became interesting, or the first time? I can't remember. Anyway, it was the last time, the previous time. And the IP of that corporation got bought out when the corporation folded, and the image networks I trained left a certain artifact in the video stream. And now a large manufacturer of video phones, if you look in their stream, you see these very similar type of artifact. And I'm convinced that the IP for that particular stuff is now buried at the bottom of a popular manufacturer's video phone. And all is written on the outside is, "There be dragons, do not open this box," because that's about the level of documentation I left them at the time. So if you want to think about neural networks as black boxes, if you want to think about machine learning as a black box, developers 20, 30 years from now might well still be running those networks that we train today. It's going to be inside a piece of software harness that's running in a virtual environment. They're like at the bottom of another stack that's virtualized onto something else, because that's what we do. We wrap previous generations of hardware and software in virtualizations, right? In abstractions, so that we can continue to use things that otherwise would have gone away.
Very interesting conversation. I let you guys speak because there was a lot of actually interesting back and forth here. I'm conscious that we're getting at the time which I think our viewers want to kind of dig into the actual technology, and I'm keen to give like Dan space to actually show this in action. But before that, I guess I wanted to kind of bring something up. Maybe we can discuss it while you do the demo. But I feel like, you know, we talked a lot about the different things that developers are looking for, and one of the things I think is the ability to optimize things without having to always know exactly what goes on behind the scenes. But I think one thing that Edge Impulse does very well is also expose some of the optimizations with the advanced mode and so on. So I like the fact you can optimize away, but at the same time you could see what's going on in the background, right? And you've just announced obviously the support for Raspberry Pi. Today you're announcing the support for Nvidia. I'm keen to actually know more about what optimizations you're enabling on models today. So Dan, maybe you can take that while you show the demo. I don't know, up to you.
Yeah, and I can talk a little bit about that now, and then Zach probably has some stuff he can add too. But yeah, I think one of the most important things at Edge Impulse to us is that we don't build black boxes, right? To some extent, any neural network is a bit of a black box because you're basically learning a representation of something in a way that's hard for humans to understand. But the stuff that goes around it should never be a black box. So if you're using Edge Impulse to train a model, things like what data set you use, what were the iterations you went through on the way to getting the model that you're trying to train. When you deploy it, how exactly does that model get run? What are all the functions that implement the different bits and pieces that run that model itself? What do those look like? How do they fit together? If you need to go in and customize them or write your own optimization for a particular platform, or if you make some fixes because this thing's been deployed running for 30 years in a project, and you're tasked with maintaining it as legacy code, it's really important that it's human readable, understandable, makes logical sense, and is well documented. And so when you export a model from Edge Impulse, you're not getting a binary, you're not getting some inscrutable lump of logic that you know is like, here be dragons. Instead, it's C++ that you can read and understand, and it's open source as well. We don't believe in controlling what, if you built something with our software, it's your thing, it's not ours. So we really feel strongly about that. And the way this translates over into the world of these targets that are a little bit larger than what we've previously been working with, like the Raspberry Pi or the Jetson Nano stuff, we've written a whole set of tools that make it easy to run models on these targets too. And they make use of the appropriate open source technologies that are already optimized to do stuff quickly on those targets. So for example, on Raspberry Pi, we use TensorFlow Lite, and TensorFlow Lite it has optimized operator kernels that have been designed to work well on that target. And we make use of that. And when you download this stuff and when you want to get it working yourself, you can make use of all of the material out there that's available to help you understand how that type of thing works. And you can read through the code and see exactly what's happening. And that's the approach that we take. We do the same thing with the Nvidia hardware that has GPU acceleration. We're using the standard tool chains there, and you can understand what's going on and see how the model is converted. You can download all of the intermediate pieces of build artifacts, so that if you want to kind of take what we've done but then diverge at a certain point and do something a bit more custom, you can do that. And you can literally go in and edit the source code for the deep learning model. So you can do absolutely anything you want, and we think that's the right way to do this.
Yeah, and I think it's important for people to understand that, like, a lot of these open source tool chains and projects aren't ready for public consumption. They're not ready for developer consumption out of the box. Like when TensorFlow makes a new release of something, it takes us several months of engineering work to make it like production ready. We have to fix things. We have to add operators sometimes. We have to deal with memory issues, make sure that it will never crash right in our cloud infrastructure, make sure it produces the same math on the outside. Like when we execute it on the hardware, the same math has to be produced as in the cloud. There's a whole bunch of things we have to do. And then sometimes we'll develop new pieces of technology to improve that. Like we have some compiler tech that we use for microcontrollers with TensorFlow Lite Micro to remove things like runtimes and unnecessary like overhead, to reduce the amount of flash and RAM that are used, because it's a really critical thing for microcontrollers fitting that. So take the best of what's there, make sure it's like really usable, and then do additional optimizations. That's our philosophy. And then make sure that's all hosted, right? Like it's click of a button and then we run and do that compilation. So like on the Raspberry Pi, the experience is amazing because you run one command line, which you'll see in a moment from Dan, and that will go pull the latest version of the model from the cloud automatically and go and take the build configuration that's appropriate for your target, whether it's like a Raspberry Pi 4 or a Pi 3 or a Pi 0. We take a different compilation build setup, bring that down to the device, and then automatically cross-compile for the hardware. And that's like many months of work to set up even those compilation SDKs yourself, just to do that manually once. And we just automate that for the hardware target. So it's a really amazing experience, but we don't hide anything. I think that's important. We do deal with engineers, developers. We can't have black boxes. This all has to be very understandable. What's going on? Why did this work? Why did this not work? How can I fix it? It's got to be something that everybody can be part of.
Yeah, and the cool side effect of that is it means that everything is pluggable. So if you have your own whole build process for your own custom hardware, because we've built things in this flexible way that's easy to understand, you can write your own build process and plug it into Edge Impulse and we'll run it for you. So everything's out there. You can go on our GitHub and look at how all of these things that are the infrastructure that runs all of these models actually work.
Awesome. I think, Dan, are you ready to show how to actually run stuff? And actually, I'm curious to see this one-liner in action.
Yeah,
that's the segue.
Absolutely. Awesome. So let me share my screen with you. In fact, I think I am sharing my screen already. Awesome. So this is the Edge Impulse UI. You may be familiar with it, you may not be, but I'm going to take you on this kind of whistle-stop tour of the key things that are important to what we're trying to do now. So what I want to do is walk you through the process of building an object detection model. And it's one that will run on a Raspberry Pi. And what an object detection model is basically is a model that not only can figure out what is in a picture, in a photo, for example, but it can localize specific instances of objects. So for example, I might want to train a model to recognize a mug because we're on Innovation Coffee, or any type of mug. I have a couple of them here. And what I want my model to do is tell me within the visual field here, where is the mug, and draw a box around it. So that's what an object detection model does. So to train any model, we need a data set. And with Edge Impulse, our philosophy is that we don't, big pre-collected data sets or standard data sets can be interesting, but you should be able to do stuff by collecting your own data and building stuff yourself with very few samples to begin with. So what we've got here in the UI is our data acquisition interface. So here you can see samples of data that I've collected and labeled before. So here I've got a picture of myself, very unflattering, with a mug. And I've drawn a box around the mug and I've told the system what it is. And I just have a bunch of these pictures. I took some last night, I took some yesterday. So they've got a few different lighting conditions and degrees of groomedness of my beard. So just got this data set here. I've only got 45 items. So this is a really small data set by ML standards, like a big full benchmark data set for image classification training or image recognition, object detection might be millions of images. But here we've started with only a few. And for a production ML project, you're still not going to need millions. If you're building stuff using transfer learning like this with Edge Impulse, you'll need dozens, hundreds, maybe thousands of items. The more, the better usually, but you're not going to need absurd amounts. So how we get this data into the system is pretty interesting. So for use with any kind of Unix device, so I'm here on my development machine, but this works exactly the same if you're working on a Raspberry Pi. We have a couple of little command line tools that can basically help you connect to the device and upload data. So here, if I run this Edge Impulse Linux command, So we're now running this client. It's connected to the microphone and the camera of my machine. And you can see now in Edge Impulse, my camera feed has shown up here. I'm using my other camera there. So I can collect some more data. So let's grab a picture of this mug. And I'll get a couple of these, might as well, while I'm here. So I'm just clicking a button. You can see they're kind of getting captured and they're appearing in my list here. But what I've got to do now is label them to tell Edge Impulse where is the mug, or what happens to be in here. So I've got my nice mug here. All I have to do is draw a box around it. It doesn't have to be super precise. And then I can tell it mug. Okay, so there's one image labeled. So I'll save that one. And what we do now is we use a bit of machine learning, even during this data collection process, to understand what it was I just labeled and try and track it in the image. And that makes it easier to keep on labeling your data set, because now I just need to kind of correct it a little bit, make sure it gets the whole mug. I can save again, and hopefully now it's going to track the mug again, and it followed me around. So we have all these little tools and tricks that make it easier to quickly label your data set. So once that's labeled, the next thing is to train a model. So I can show you the interface for doing this right now. So here we're training an object detection model. And what this does basically is it takes the image as an input. It applies a lot of mathematical transformations that it learns how to do during training. And then it outputs a bunch of bounding boxes onto the image that basically tell you where any objects it detected were. So here I've just got all the default settings. That usually is a good place to start. We pick sensible default settings so you don't really have to worry. And I've already trained this model, so I've got some information about the model here. It's getting about 83% precision. So that's a score that we use to understand how accurate it is at putting the box around the mug correctly. And it's about 3.6 megabytes in size, which is too big to run on most microcontrollers, but it is absolutely going to run great on a Raspberry Pi. So you have some tools here as well, and levers that you can choose. So only the developer, only the engineer knows how to understand whether something is too big or not accurate enough. So there are lots of different optimizations that can be done to make deep learning models smaller, maybe sometimes at a cost of accuracy. So here you can choose which version. So we have a slightly more accurate version of the model here, which is unoptimized, which is 10 megabytes. So that might be the one you want to use on your device. If you've got enough space, that could be good. But if you don't really care about that little few percentage of precision and you want it to be small, you can pick that one. So the next thing I can do in my flow is go to another command line tool. So this one here pulls down the model, it compiles it for the device that you're currently on, and then it runs it. So this exact same command line utility you can run on your Raspberry Pi, you can run it on your Jetson Nano. If I hit that, it's going to start running the model, and it will start printing to the screen what the model's detected. So right now it's not detecting anything, but hopefully if I hold up a mug, it's giving me some bounding boxes. So you can see this is what you would use in your code. It's telling you, hey, this was a mug. This is the probability of whether the mug was detected or not. So if that's low, you know that the model has low confidence that it's actually a mug. All of these are pretty high. It's a fraction of 1. So this is a pretty confident probability that it's a mug, and it tells me a bounding box of it. And so this is kind of boring to look at them scrolling past, but this would be how you integrate with your own application. And to make things more fun, we actually run a little web server as a part of this command line tool. And I can load that up here. So we're capturing the data. There I am from 2 different angles now. And hopefully when I lift up my mug, it's able to recognize it. And it's not perfect. I only gave it 45 samples of data, so you can't expect it to be perfect, but it's doing a pretty good job with this mug. And hopefully you can see if I pull up 2 mugs here, still not perfect. I didn't actually have any samples with me holding both mugs, but it's able to do a decent job of detecting these things. So that's as easy as it is. And so we've got now a closed feedback loop of, first of all, we captured some data in here. We captured a small amount of data. We then trained a model. We got some information about how the model was performing there on our data set that we're training with and how big it is. And then we're able to deploy the model down onto a device and test it out visually. It takes minutes. And what we can do now, because we've got a feedback loop, is I can now think, hey, sometimes it's not capturing this mug. If I have it at this funny angle, it doesn't recognize it's a mug anymore. So maybe I need some more data set that covers the mug being at this funny angle. And I can retrain my model a bit more, and it will hopefully understand that a bit better. And I can test it out again. And you can also set up a test data set in here so that rather than having to go in and play around and experiment, you can have a data set which you're able to run inference over, and it will give you a percentage score for how accurate the model is. And you can do all sorts of other stuff too. But you see hopefully how quick and easy it is to just have this feedback loop, which is what all developers are familiar with, right? And prior to this kind of technology, the feedback loop involved setting up all of the machine learning stuff on your workstation, running some obscure scripts, somehow shoehorning this into a model that will fit on device, deploying it on device using some more scripts, and then going back to the beginning, even capturing data, pulling it off the device takes ages. But now you can do all of this in a bunch of simple command line tools that will work on any Unix device with support for a USB webcam. So hopefully that gives you a little glimpse into how easy this is. You know, if you are interested in trying this, which I hope you are, we have a ton of documentation and blog posts and videos, whatever kind of content you enjoy. We've got all of that out there, and you can head on to our website or follow us on Twitter. You can see any of this stuff and try it yourself, and it literally will take you minutes to get started.
What I love, I mean, we were actually talking before my power went off. I was actually in the TinyML Tuesday, the online Twitter Spaces, is it called? That you did, right? And you were actually mentioning that a trick or a tip for everyone doing machine learning on edge devices is usually to run stuff on your laptop or on another machine that is more capable, so you don't have to worry about the optimization right away, right? And I think this is super cool that you could run stuff on your computer, check whether the recognition or whether you've got enough samples, whether you've captured enough data, the right data, and so on, and then think about the next steps, right? I think that's super relevant, and it's good that you can do that all in the same tool. Really like that.
Exactly. That's one of the things you get if you can use the same tools everywhere. Then the skills that you learn working on training a model on your laptop are going to apply to training a model on an embedded device. And it's not the case that you're context switching all the time, which we all know is like a nightmare when you're trying to build something. You just learn one set of tools once, and the same tools work everywhere. And we take care of the tricky parts that allow you to have that kind of universal experience.
So I loved it. Thank you so much, Daniel, for providing that demo. Awesome. I hope everyone else watching loved it as well. There is a question that popped up from the infamous David W., who loves talking about autonomous vehicles in particular. I'm going to bring it up here real quick, and then hopefully, still on the theme of the demo that you just provided. Are there Edge Impulse autonomous mobility examples out there, like lane following? And then note to Dan, if you are ever in the Michigan area, you should definitely reach out to David. I can get you his contact information. But addressing the first question, are there any autonomous mobility examples out there, like lane following?
Yes, we actually have on our blog an example of doing this with a little robotic car. So let me see if I can find that. It was quite a while ago, so I'll have to do some scrolling.
That's all right. We can also take that, take the link when you do find it. We can take it, put it in the description. So, David, check out the description of this video once it releases after the stream. You're muted, Alessandro. There
you go. There was another question actually from Amit. I I'm not sure exactly what he was referring to, but I imagine it was referred to having a tool that allows you to deploy your code, your model on any hardware. I think it was, I'm assuming it was related to that because it was earlier on in the chat. Does anybody have any thoughts on that?
I can take that one. Like by in the future, we meant like this week. So we can do lots of hardware. We can deploy it today. So I'd say that the vision of this is starting to come true. What you'll see happen in the next few years is that we'll be able to target more and more hardware, even exotic kinds of accelerators. So I think when you talk about future, it is going to take a couple of years for all these new accelerators and architectures to bubble up from the silicon industry. And of course, from the software and tools and open source community, we're going to keep up with that. So I'd say a couple of years, you'll see like all the new kinds of variations of hardware pop up, and then we'll get pretty good support across that.
So how hard do you think the optimization task is going to be, right? Because if you're optimizing for a microcontroller as opposed to a Linux desktop type machine, you're very much restricted by the architecture of the microcontroller. So the Raspberry Pi RP2040, which we're looking at, doing ML on now, there is a lot of optimization. We have reasonable results, but we're looking for there's a lot of optimization to be done based on, for instance, the flash memory size and the on-chip SRAM size to the size of the models you do. So that's going to be very chip specific, isn't it?
I'd say it's more like class of architecture specific. So for example, in microcontrollers, we cover the entire Cortex-M range of devices with a lot of our optimizations. And that's another reason why we use source code, why we have C++ source code.
Yeah.
We have a lot of compiler optimizations in there. So for example, we use a lot of SimSys NN and SimSys DSP. So the work that ARM already is doing in optimization, we use that. But at the same time, like TensorFlow Lite Micro leaves a big runtime with a bunch of overhead there. So this is where we apply like compiler techniques to remove some of that and go down just to the math. So there are things you can do that are pretty generic. And then there are things you can do that are very device specific. Like if you have a specific type of register or vector extension that you can leverage in a device, then we have to go and implement the operators and kind of take a branch that we use for that. And that just takes collaboration with the industry. So for example, what we do is we collaborate with the silicon vendors, or sometimes we'll collaborate with ARM, for example, or with Nvidia to go and like build in those kind of special additional tweaks. But I think the important thing is like make it work on, for example, Cortex-M more broadly, and then do additional optimizations on top of that. But the nice thing is they all flow down from the digital twin math, right? Like that does not change all that much, regardless of whether you're on like a Pico 2040 or a Cortex-M7 ST part. There's like little tweaks that we're making to make that even better. So luckily we can always default back to like the thing that works. We are going to see architectures that are restrictive. So the one exception here is that we see things like neural processing units that, for example, only do fully connected networks. We do see that from time to time. And that's something we have to take into account in our UI and our tools. Like if you choose that hardware target, we'll tell you that, no, you can't run CNNs on this target. You can only run fully connected, and we'll kind of just restrict the UI experience down to that. So that's the one exception, but there's not many of those. Most of the hardware we're seeing is pretty generic, running most different types of ML architectures, including classical, most DSP stuff as possible.
Yeah, one tiny thing I'd add there, sorry, is there's also the idea of can you vary your network architecture and the type of model that you're running depending on the type of device to get better results given that device's particular constraints, whether it's got lots of ROM but not much RAM, lots of RAM, not much ROM, fast processor, slow processor? And the answer is yes. And we're working on some really awesome tools that can do that kind of experimentation for you. So it can, given a data set, arrive at the type of network architecture and configuration that will work best for that data set. So this is all exciting stuff that's in the pipeline.
And I was just going to add to that. Great question, Alistair. I think that's super interesting, and it's something that everybody should kind of try to understand for themselves when they're trying to develop a model and maybe they've got different targets. One thing I'll say is that obviously ARM is working closely with Google, and all the CMSIS optimizations have actually gone in the main line. So when you do pull from Google, you do get the optimizations for the specific core or not, or if there isn't an optimization for the specific core, it reverts back to the operator, the standard operator, and the standard operating implementation. The other thing, obviously, there is a lot of workaround tools for the various different accelerators that we've announced are going to come out soon. So there is all that, and I think the last point that Dan made is really interesting as well. Is can you optimize the model? And we see a lot. For example, the feature extraction can be very clever, right? So if you have more clever feature extraction DSP code in there for sometimes like the more constrained devices, you can get better performance. So perhaps like kind of mix and match of different feature extractors and classifiers could help in that space. And I imagine Dan, I don't know exactly what you guys are building, but it sounds interesting, and perhaps we'll have you on another episode talking about that in the future.
Yeah, absolutely.
I'm just conscious of time, Dan. I don't want to cut you off, but we've run out, and we're 3 minutes over the hour. So I just wanted to have everyone maybe say a few last words and then close out the episode. Maybe you could just go around. We can start from Alistair, that's unmuted. Have him say any last words, any shameless plug, and then we move on.
Well, I guess that my shameless plug is encouragement for Edge Impulse to support the RP2040 and the Raspberry Pi Pico. That should be your next task, guys.
Awesome.
I second that.
I can tell you the C++ will compile right now. You can go try it. It will compile.
Okay.
It might not be fully optimized, but it will compile. So try it out. The plug on my side is that we're entering the era of machine learning for all developers and engineers. This is the time to start getting your hands dirty, start learning what this means. You don't have to become a deep ML expert. You're going to become a domain expert for what it means for you, the stuff you work on, right? The data you work with, the sensors you care about. Start learning about what machine learning can do for you and start to leverage the tools, and then give us feedback, right? All of us, right, would love feedback on the stuff you want to work on more, and we can make that better for you.
Yeah, I'd like to just echo what Zach said. This is a moment where a whole new set of capabilities are becoming available for developers who didn't have access to them before. And these developers, all of you who are watching this, are people who know a great deal about specific things. And the thing I'm most excited about here is that suddenly these tools that are incredibly powerful but have been of limited utility and limited access to most people are suddenly in your hands. So now's the moment to go out there and learn how to do them and see what kind of crazy stuff you can do.
I love
awesome.
it.
Robert.
Yeah, no, I love it. Thank you all so much. I mean, your time is obviously valuable. We appreciate that you spent this hour with us. Thank you to all of our viewers, of course. And, if you have any other further questions, we did post something in the chat there. If we missed your question by accident, or if you'd just like to leave some feedback on the show, please feel free to post that in the comments once the episode posts after the stream. But yeah, Alessandro, back to you. Let's close it out. I opened it, so I'll let you close it. And thank you, everyone.
I'm just going to relink the link down here. The Raspberry Pi blog, awesome blog from Alistair, as usual. Always interesting and full of information. He's actually linking in that blog to all the performance analysis that he's done in previous work as well. So very interesting. Go check it out and try out Edge Impulse. And any questions, leave them on the bottom of this chat or the various forums that we all have. So, looking forward to your questions and answering all your questions. And thank you all for watching today. And thank you, guys, Alistair, Dan, Zach, for being with us. And as usual, for being awesome guests.
Thanks, guys. Cheers.
Thank you so much, everybody. Have a great day.
Thank you.
Bye, everyone. Thank you.